Welcome back again. So this time what we're going to talk about is some variable types. A little joke here about how variables used to be thought of and how you should really be thinking of them now. Not really too important. Important thing you need to know is that everything is stored in ones and zeros. Said this a couple times. True on the PIC microcontrollers, true on any computer you use. Everything goes in as ones and zeros. So when it comes to numeric data, there are two real ways that things are stored. One is as an integer, which you've seen a couple times, right? So this is the binary storage using the 2's comp for the negatives. With integer storage, only whole numbers can be stored, so you only get the whole numbers. There is a thing called signed and unsigned integers, which we kind of mentioned last time, but not really that detailed. Really what it comes down to is every time you write like the word char, you actually have a word in front that's either the word signed or the word unsigned. If you leave it off, it defaults to signed. But if you ever wanted to, you could write the word unsigned. And what that'll do is that'll give you a bigger range of positive numbers that you can use, but you can't use any negatives at all. But sometimes people use unsigned char or unsigned int or unsigned long to give themselves more positive numbers because they know it's a positive. The names for the three different integer data types are char, int, and long. Char is the only one that ever confuses people because they think, oh, it has to be a character. It's like, no, it just is 8 bits. And so it's called a char because it actually fits a character very well. Better names would, of course, been like int 8, int 16, int 32. Would have been way better names. Oh well. They have perfect accuracy, which probably doesn't mean much to you until you start looking at how floats work. And speaking of floats, what they are is they are, of course, things with decimals, like to the right of the decimal point. So like a half, a quarter, things like that. They are always stored in essentially scientific notation, but it's binary scientific notation. Instead of like some number times 10 to the power of something, it's some number times 2 to the power of something. And that's kind of how they're internally stored. As far as the limits go, they use 32 bits on a PIC. That's whether it's a float or a double. They mean the same thing on the PIC. They just mean it actually... A double is just a float, if you know what those words mean. The range, even with scientific notation, it still has some limit. They can go up to about 10 to the 38th power. So that would be like a number with 38 zeros behind it. Could get stored as a float, but don't try to go bigger than that. Hopefully that's not an issue for you. But there is a limit. And you'll notice that they do not have perfect accuracy. So this is not written here for a reason. They are approximations. So let's look at both in a little bit more detail. So first is, I kind of like this. This is what's called a memory model. So this this little matrix here is like looking at the map that would be stored in a PIC. If you said that you had a char, you called it x, it had the value 1, that would actually get reserve 8 spots in memory, and it would put the 1 in there. Likewise, if you had 2 and then 3, it would reserve the correct number of bits in memory for a char, which is 8, and then it would put it in there. If you said int, it would, of course, block off 16 bits in memory, and then it would put it in. So this is 1 as an integer, and it puts it in there. For some reason, this picture just like totally makes it sink in for me on how things work. If you had a floating point, so the first thing to remember is that floating points are stored with 32 bits. And so this entire chunk gets taken away for the floating point. If we wanted to store 0.1, we'll talk about this in a minute, but the way they break down is there's 1 bit used to store the sign, 8 bits used to store like the exponent, so that's like the times 2 to the power of something. And then there's actually the remaining, it works out to be 23 bits, or what's called the mantissa, and I'll get to that when we get to the slide. And that's like the something times 2 to the exponent, right? So that first part is the mantissa. So the first thing you need to know about integers is you have to really know these ranges. So there's some blanks here where you should go ahead and fill in on your notes exactly what the ranges on these things are. So we'll just kind of do the first one together, and then I'll just kind of unveil the boxes. So if we've got 8 bits in an unsigned world, the min in an unsigned world is 0. The max would be like all ones. And since it's unsigned, this is totally legit. It's 255. In a signed world, you can have negatives. You may recall that it goes down as low as negative 128, but it only goes up as high as 127. So that one's fairly easy. We actually just went ahead and did it. I kind of like to write it in binary and to write the decimal beside it. A little neater though when I did it in advance. You can see what these things are. So that's with 8 bits, signed and unsigned. 16 bits, concept is identical. It's just that you have a lot more bits to worry about. So you have 16 zeros, 16 ones. Unsigned ints can go up to 65,535. You'll see that number a lot. If it's signed, it has this range to where it can go up to 32,768, 767, I guess, on the positive side. Then longs are 32 bits, so they get pretty long, right? Like I can see where the name came from. It's pretty long, and they can get up to essentially 10 characters long. So it can get up into the, what is that, billions? So it can get up into the billions quite comfortably. I always like to remember that, like, if I just take my keyboard and I just like go across from like 1 to 0, that number would fit as a long, right? Like that's totally valid. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, that fits. Of course, whenever you sign it, you've got a limitation on both sides. So most times long is going to be plenty long for the integers that you need, and it's very handy type to use. Just to mention a couple integer overflow things. So if we had, I just kind of set up 2 characters here. One is an unsigned character. It's X, and it's currently got a value of 1 stored in it. The other is, it didn't say character. On our compiler, if it doesn't say, it defaults to signed, which is kind of nice. Some other compilers for characters that default to unsigned, don't need to go into it. Ours always defaults to signed. Same with int. It defaults to a signed int. So these things are in there, happy-go-lucky. Let's go ahead and throw some things in here. What if we tried to put 200 into X? So 200 into X, what's it look like first? 200 looks like this. So just like that. And since it's an unsigned, it'll go in here just fine. You know, you can override these if you really feel the urge. And if you pull it out, you'll get 200 back out, no big deal. If you tried to put 200 into a signed, it would actually put the exact same things in. So that was what, 0, 0. Except for when you try to pull it out, 200 is outside of the range, right? Because it went from negative 128 to positive 128. When you try to pull it out, I think it comes up to be like negative 44. So if you try to pull it out, that's the number that you actually get out because it was too big. Likewise, if you put in 260, 260 I think I wrote down earlier, it kind of looks like this. This of course won't fit. So if you try to put this number into there, you're just going to lose that top one, and you're going to get left with just the bottom 8, which we talked about last time. And I think that turns out to be 4, right? So if you tried to put in 260, you would just get 4. You have the same problem with integers. It just doesn't happen until a lot later, right? So if you tried to put in the number 32,769, turns out that 767 would have fit fine, but 32,769 turns out to be a negative. So if you put it in, it would put the number in there, but then when you pulled it back out, it would pull back out this negative number. All right, beating a dead horse. We talked about the last.